So our contribution to this special issue was on modulation and coding for non-orthogonal multiple access and rate splitting multiple access. The paper includes an introduction on the subject and introduces different NOMA structures, including its design for symbol asynchrony. We also discuss the traditional modulation and coding schemes and their applications and shortcomings in NOMA. We have a section on machine learning for modulation design for NOMA, and a section on rate splitting multiple access. Finally, we discuss open problems in this area. In general, the main idea behind NOMA is to send more than one information over the same wireless resource. NOMA can be used both for downlink and in uplink. NOMA can facilitate more connectivity with concurrently serving multiple users. However, it has its own challenges. For example, inter-user interference, synchronization challenges, and its sensitivity to channel state information. In this talk, I will discuss the first two challenges and some ideas to address them. Here, I show a simple example of power NOMA for two users, in which we superpose the symbols of the two users by allocating different powers. At the receiver, the stronger user first decodes the signal of the weaker user and then cancels its interference using successive interference cancellation, and then decodes its own signal without any inter-user interference. The weaker user will consider the signal of the stronger user as noise and will decode it, which results in inter-user interference. This is an example of how to implement the idea with traditional modulation schemes. So in this example, we have a 4 PSK constellation shown with these black pluses that is used for the weaker user. And then the signal of the stronger user is encoded using these 8 QAM constellations. And when we superimpose the two, the result is this 32 red QAM constellation that can transmit the information of both users. At the receiver, so when we receive the signal with noise, so first we decode the signal of the weaker user, and then we remove that from the received signal. We cancel its interference, and then we can decode the stronger user's signal. So like these examples, most work in the literature assume perfect synchronization. However, one question is it possible to synchronize all users when you have a multi-user scenario? And a more important question is, even if it's possible, is it desirable? Is there any benefit to have such a synchronization? So to answer the question, let's look at a simple two-user uplink NOMA example in more details. With perfect synchronization, the received signals of these two users is a superposition of the transmitted signals. And when we sample at the peak of the pulse shape, we will have a linear combination of these two signals. And to manage the inter-user interference, as I discussed, we can use successive interference cancellation for decoding. On the other hand, if we have a symbol time asynchrony between the two users, we receive signals like this. So now, in addition to inter-user interference, we will also have interference when we sample at the peak from the symbols of, for example, previous times. So that causes inter-symbol interference in addition to inter-user interference. However, if you look at the sufficient statistics for such a system, you can sample at the peak of each of these two pulse shapes, and that will result in two sets of equations, one at the peak of the first signal for the first user, one at the peak of the signal for the second user. And this is what we call sampling diversity. And in fact, this sampling diversity will enlarge the rate region of the uplink NOMA. So, and as a result, the benefits of sampling diversity is more than the disadvantages of the inter-symbol interference. In this figure, the black pentagon is the rate region for a synchronous system, and the red curve is the rate region for the asynchronous system. As you see, this is enlarged, which means we have more capacity here. In fact, you can even design practical coding and modulation schemes to achieve an operational rate point like this, which is outside of the rate region of the synchronous system, which means you cannot achieve this with any synchronous NOMA scheme, while you can achieve it with these coding and modulation schemes for asynchronous NOMA. Well, similar approaches using superposition coding, successive interference cancellation, and sampling diversity works for downlink asynchronous NOMA. However, for downlink, since we have access to the signals of both users, we can design pre-coding and post-processing techniques in addition to asynchronous transmission to remove the inter-user interference cancellation from the signals of both users. And there's no need for successive interference cancellation if you use these pre-coding and post-processing techniques. These techniques also tremendously enlarge the rate regions for the downlink NOMA, as you see, compared to the rate region for orthogonal multiple access methods. You can gain a lot using NOMA. And with that, I conclude my talk. Thank you.